So you heard from BPP on the first day about RAG and about improving search with modern technologies, and they're going to do a deep dive today for you. So we're going to have Matt Purcell and Brian Tran talk about going deep on RAG.
Good morning. Happy Thursday. How's everyone feeling? Good. This is the core group, I can tell. You guys excited for transport? Anybody? I'm excited. I know you're excited. We're excited. Excellent. So today we're going to be talking about search tooling. And what is search tooling? Search tooling is essentially a flavor of RAG, which we'll get deeper into. And RAG is essentially how general-purpose large language models search data. It's one of the methodologies. So we're going to be talking specifically about search tooling, but to get there, we need to talk a bit about LLMs. So what does the LLM space look like right now? Well, it's highly competitive, and I think everyone who probably reads tech news understands that. Claude, required around $20 to $30 million to train. ChatGPT 40, which looks kind of like 4.0, around 100 million. Gemini, around 100 million. Llama 3, over 100 million. And 50, ChatGPT 50, it will be north of $500 million by the time it's trained. So what does this mean for us? Well, as application engineers and software engineers, it's an amazing time to take advantage of this capital investment by these companies, these large amount of dollars that they're going to continue throwing at artificial intelligence. And what we're going to talk about today is how we utilize these general purpose language models in our application and how you can possibly utilize them in yours as well. And what we'll discuss is that we don't usually choose one model. We choose model sets. We don't always have the AI be the force generating the response. Sometimes we switch it to the application and the API. And we're going to talk about these different techniques and how you can really leverage these models cheaply. Because the first thing that people think when they hear about a 500 million model or a $500 million north model of ChatGPT 50 is that it's going to be expensive. And there's nuance to that and some truth. Yes, it's expensive to train, but what we see is when there's these new large leaps, like 50 will promise, there's what's referred to as model distillation. And that's where smaller models like Mini and Nano, which is just released, are trained off of these larger, more accurate and smarter models. And once this model distillation occurs, which is just one technique to create smaller artificial intelligences off of larger ones, they end up being cheaper and faster, although slightly less accurate than the parent. But if you can think 5 years into the future, the distilled model of ChatGPT 50 will be leagues above the ChatGPT 40 model that we see today. So let's dive into search tooling. My name is Matthew Purcell, and I'm the Director of Engineering at Broker Public Portal.
I'm Brian, Senior Software Engineer.
Yes, and we are one of 4 engineers at BPP. We've been working here for the last 10 months, and everything that you're going to see is really stuff that we've crafted over that time. So in order to talk about search tooling, I have to show you how we're actually utilizing it. So on our broker data website, we have this smart filter bar. And you can see you can just type in natural language search text. And what we do at the end of the day is we distill it down into RESO fields. And this is why RESO is so important to us, is we needed a map to figure out how to take the natural language search and distill it down into structure and characteristics and price groups that make sense for search. And that's exactly what we did here. And that was completely dependent on the work that was done in the data dictionary groups and transport groups over the last 5 to 10 years. We would not have been able to build this today had folks not been working on this for so long, and we're going to talk about exactly why that's the case. This same search, which works in English, also works in Spanish. So underneath our smart filter bar here, you'll notice that when we search, it can take any language. And that's because one of the first things we do is language detection. Certain models are better at working in certain languages. As long as they have real estate domain awareness, we have the ability to swap models underneath the smart filters bar. ChatGPT today reports itself, at least on the 40 model, of having knowledge of over 50 languages and semantic meanings inside of it. Gemini self-reports at over 100 languages. So not only can we use these different models in isolation, but we can create a superset of what they're both good at by understanding which languages work for real estate and swapping the models underneath. So let's take a look at that search. And this breaks into what we'll call a feed-forward pass later on. But if we take this search, I'm looking for a 2-bed ranch-style home for less than $600K with a price cut, and HOAs fees less than $300 a month. We can distill it down into what we call keywords, concepts, and there's also spatial search and hybrid search. When we look at this search, we take a look at the 2 bedrooms, the less than $600K, and the HOA fees less than $300 a month, and we determine those as lexical constraints on the query, right? Let's say they're looking for a 2-bedroom. Is it a 2-bedroom exactly, or will a 3-bedroom suffice? We have to determine that constraint, but we assume they certainly aren't looking for a 1-bedroom house. Ranch style, is that referring to an architecture style or a way of living? Right? We have to make some assumptions when we're distilling down and snippetizing this natural language search text. The less than 600K, again, that's a very lexical, something that we would search on with a constraint. And the price cut, are they referring to within that listing history since it's been on market or since the previous time it's been sold? We, again, need to make inference. The HOA fees less than $300 a month, will they be willing to accept an HOA that if there is no HOA, or that HOA fees are less than $300, and we typically go in that direction. So you can see we distill this natural language text into keywords, concepts, these constraints, and from each of those we figure out how we're going to determine the query. So for keywords, we typically use Elasticsearch and we use match with separate analyzers underneath, and that's using BM25 under the hood. And just because it's a keyword match, it doesn't mean it's a like statement, right? We're using natural language processing, we're using fuzzy matching, we're using string distance, all these different tools to get the consumer where they're trying to search for. When it comes to concepts, which we're going to see on the next page, like fixer-upper and luxury, that's where the semantic, this dense and sparse vector search really shines, because there aren't always lexical keyword arguments associated strongly with a concept. Spatial search is the intersection, right? Polygon type search, point to poly, and we can combine that with lexical matching to get a really good approach. Hybrid is where we mix these retrieval types, and if I could talk about that for just 1 second, I would say that all of these approaches have drawbacks. For the keyword search on the ranch style house, if the agent hasn't entered that it's an architecture style ranch, they will get a false negative, right? They will not get a return result. So we have to work with that on the constraint side. On the concepts, we see the exact opposite. If someone types in no HOA in a low inventory market in vector space, right, in ours it's a 768-dimensional model, in that space, no HOA and HOA are very close. So you're going to get many false positives back in your return set unless you spend a lot of time creating cutoff scores. And hybrid can have the best of both worlds or the worst of both. You can have false negatives and false positives in hybrid retrieval when done incorrectly. So let's break down the few real true semantic concepts that we see. We see these concepts such as fixer-upper and luxury. And why are they concepts? Because underneath, right, a fixer-upper home could have 1 bedroom, it could have 10 bedrooms, it could be a mansion, it could be a mobile home. There isn't a lexical keyword inside the RESO Data Dictionary that strongly relates, or a set of attributes that too strongly relate to the concept of fixer-upper. And the same thing with luxury, right? It could be a 1-bedroom with an infinity pool, or it could be a 10-bedroom mansion, right? But what we find is, on the sell side in the listing agent public remarks, where they include some constraints and obviously fill out the rest of their listing data, we see selling by concepts. And it makes us, in some ways, sometimes overrepresent the impact that that has. We see selling by mountain views and city living. We see downtown vibes and urban living, right? We see, rural and quaint. These are the concepts that agents use to sell in conjunction with their constraints. But on the prompt side in the search bar, what we see is constraints. We don't see users entering luxury in a market. We see them entering the number of bedrooms they're looking for. We don't see them looking necessarily for a fixer-upper with those exact words, but they might be looking for pre or post remodel. So there are trigger words that we can use to indicate it's supposed to be a conceptual search. But the vast majority of the time, we see search by constraints. Because as a consumer, I rarely buy just by the term luxury. I buy by the things that mean something to me. And that might be the number of bedrooms that relates to luxury or the list price. So what should search be? As we're kind of building this out and we're looking behind that smart filters bar that you saw, and this is the text being entered, there are some things that we strive for, especially when working with general purpose large language models. Search needs to be fast, accurate, and appropriate. Fast, for autocomplete speeds, we strive for under 100 milliseconds. That's under the blink of an eye. For smart filters, we accept up to about half a second. Because after a second, right, if it's a long inference, a user's going to drop off your website. No one's going to wait. So you can't accept models that are going to take a long period of time for inference on the search side. They need to be accurate. If an agent goes to a house that has, that looks like no HOA and finds out that there's $500 of HOA fees and lose the sale, they've not only lost that client, they've likely lost them for life, right? That wasted everybody's time. So we want to make sure that the responses are accurate. And lastly, appropriate. This goes into some of the concepts of AI of helpful, harmless, and honest. We don't want to allow people to search by protected demographics. We don't want people to be able to search by things that violate fair housing law. We don't want to allow agents to be in that position. When we execute our search queries and we cannot decide if it's a concept or a constraint, we defer to lexical constraint style search. And that is because we try to limit false positives more than anything else. In an ideal world, we join those sell-side concepts of that mountain living or that fixer-upper and the luxury with the buy-side consumer inputs when we can relate the two. So we're going to take a look at part of the heart of what makes this work, and this is a basic completion model and what's known as the feed-forward pass. And I'm using this terminology because it's the same terminology that's used by the architects of GitHub Copilot. So if we see here, right, we have a user prompt, and the input goes to the application. And I talked about snippetization a bit, right? And the first thing we're going to do is we're going to break down that text and score it. We're going to determine that concept versus constraint versus spatial versus hybrid style search. We're going to do prompt assembly with a basic prompt that we have set up, and we're going to incorporate the user input. We're going to decide whether we want to use zero-shot or few-shot modeling, which means do we want to give it no examples of how to do the output, or do we want to give it pre-made examples of what the output response should be like? We'll add chain of thought, act and react techniques to allow the model to have extra time for inference if we desire in our application. We can ask it to think about its previous response, which is known as react. LLMs think by writing out loud. There is no real internal monologue, so they need to go over their initial tokens to have a good concept of what they're executing on. We look at content moderation on the application feed-forward pass. Is it violating fair housing law? Right? Then we are not going to allow that input to go through. And if we've seen this input before, we can incorporate feedback scoring for similar or exact previous user inputs. When this prompt goes through the large language model, we end up on the completion side, where again, we have a set of options. We can mutate the response, we can look for keywords or hallucination trends that we wish not to exist, and try to catch them. We can use another LLM as a judge for the inference of the first, much like a department and organization. We can have one LLM in the role of QA and another on executing the search request. For us, LLM as a judge would have been far too slow to incorporate in, but for applications that are allowed more time on inference, it is a great opportunity to add. So as this gets bigger is where Brian starts to become a really big part of executing and making this happen. So the first thing we started was completion with RAG, or Retrieval-Augmented Generation. And this is where we allow the LLM to retrieve information based on a tool set or function call that we've defined underneath the hood. When it does this, right, we're giving it a structured way to search on data. Now, if the LLM had all of the information inside the prompt, right, it has other issues such as needle in the haystack. If it had all the data in its training model, perhaps we wouldn't need to search. But what we see in listings especially is highly dynamic, updated listings, which means there was always going to be a place for retrieval-augmented generation in search in real estate. The RAG reaches out to the API or the LLM, which grabs the data from the database. Brian constructs that argument and brings it back to the LLM, where then we take that response and we generate from the LLM back to the user. So we retrieve through the tool, we augment what the LLM knows, and we generate a response back to the user, which is the heart of RAG. So how do we take this one step further? We did what's called completion with search tooling. Now, it's a very similar feed-forward pass, but what we stop is the LLM doing the augmenting and the generation. We simply use the LLM to take a look at its tool set and figure out, based on the natural language text, what tools and parameters would I choose. We then send those to the application and back to the API, which now has to do more work, and we allow it to execute on the tool set. We allow it to generate the response. And why is this so important for inference? Well, an output token is 3 to 5x as expensive as an input token on the prompt side. So by minimizing the number of output tokens, by pushing that to the application, we can lower our cost of inference dramatically when using these general purpose large language models. So this is where I hand it off to Brian, because we create the tool from this general LLM, we determine what it is, and rather than letting the LLM act, we switch it to the application and the API, which Brian built.
So if you think about search and like when we're looking for things, that's how users find things, right? And APIs are how machines find things, because it's an application. I forgot the acronym, but it's an interface where how machines can look for things. Yeah, and why it matters for search, specifically the RESO specification, the standard fields and the consistent semantics, the definitions for, list price, for instance, we know that it is a number, and that helps out on your front end of choice if you're building like a mobile application or a JavaScript front end. Another thing to think about is like the string versus string array, right? Now we have different types. That is not consistent, and that can present problems. When you have a string or a string array, you can operate very similarly. You can iterate through it, like what's first, second, third. You know the length, but when you go to maybe operate on it, but have two different values for a field, you can run into unpredictable errors because it's not consistent, right? So it helps standardize. Standardization is not just about consistency. It directly impacts the quality of search and retrieval. It makes it easier for everyone. I'm just an engineer, but the UI team will thank you a lot, especially the mobile team, because mobile appreciates a lot more type-safe APIs. So where we also use OpenAPI, previously known as Swagger, as a source of truth for machine-readable APIs, because we are defining a specification of how the API works. It's in a structured format. Like this is the query parameter. This is the HTTP GET request that you should be using. It's documentation, but it's a lot more than that, right? I think it's a force multiplier if you use OpenAPI specifications, because you can generate client SDKs in any language, whether it be Rust. I know some people in the room use Rust. Shout out to Zenlist. You can mock APIs. So when I'm really slow at making APIs, my colleague can mock the API because we know the types, we have some descriptions, and he can work without me when I'm out on vacation. And I can validate requests and responses automatically, right? There's a lot more tooling out there in the free and open source world, like cybersecurity. You can use OpenAPI, the specification, to make sure that your API is a little bit more safe in that regard in terms of security. It's a big force multiplier for, I think, us developers. So taking the prompt to the API, When we think about it, users can use natural language, but on our search page, we also give them the option to use the filters as well. Because sometimes, having the option is nice. So we need to take the natural language and use the AI to map the intent, what does the user mean, to an API call using the open API. Because it defines the query parameters, it defines what is available to it, along with the descriptions. And under the hood, that's just the RESO specification, because that's what we have kind of in the database. And it becomes self-describing for us developers and the machines, the LLM, and it feels like magic, all powered by standards. So tying it all together, the RESO specifications defines the data model. This might be the model that's stored in your database. The API, the specification, the open API specification makes it actionable, gives me documentation, gives the LLM documentation on how to operate against it. The search tooling, whether it be lexical, neural, or hybrid, makes it discoverable. And AI makes it natural. AI with RAG makes it natural and adaptive.
Awesome. So how did we get here? We didn't just, because we're in Amazon, use a model in Bedrock. We didn't limit ourselves, because we're in GCP, to a model in a Gemini model. When we're choosing a model, we really want to look holistically at the entire model sets that are out there, and we start to narrow them down. And the first thing I would say is it's very easy when you're in a cloud provider to be locked into certain models, because that is their moat, right? If the model is the product, the distribution is the moat. So what I'd recommend is ensuring, as long as it's easy to use, that you're using things not just inside your cloud provider, but as many different models as you possibly can that make sense to try. Because you might not just pick one model. LLMs are inherently fallible, right? And they don't have the best uptime. You're likely going to be rotating through models and providers under the hood. So let's break down natural language search with smart filters is what we built and what we asked of our LLM. And we asked quite a bit. The higher the bar on here means the more demand we had from the general purpose large language model. Intelligence-wise, we needed to be fairly smart, but this is actually not the most difficult exercise. And the reason it's not that difficult is because the 1.7 training data is embedded in many of these models today. And I'm going to show you how we prove that through an eval harness. But when we took a look at ours, we said we need something moderately intelligent with an understanding of the real estate domain space. And it needed to understand some fair housing law, although we could add some of that on the prompt side. The latency, we needed to be very, very low. And I know it looks inverted, but this is a demand chart. Correct? So we're looking for very low latency. We need that under that half a second, and that includes the time to the API. Cost, when we look at throughput on our smart filters, we're looking and are projecting in millions of requests, millions of unique requests. So we need to ensure that the inference is extremely low. The inference cost is extremely low. And easy to use, we don't want something that's going to be hard to maintain. We don't want something with a lot of breaking changes. We want something that was pretty palatable to add in our application, and many of the LLMs on the back end are. And accuracy, we need it to be very accurate, but not perfect. And this is where a lot of the front-end UI work comes into play. When we break down into those pills, if there is a misinterpretation, if there is a hallucination, it's reflected back to the user, not as a score or a probability, but as a physical pill they can exit out. And this allows us to work with the fallibility that LLMs present. So when we're choosing a model, the first thing we realize is we're not actually choosing a model. We're choosing a problem. And we want to break down that problem to really understand how we're going to apply an LLM, and if we need to, right? Is the problem summarization over large amounts of text? Is the problem classification, which ours generally is? You should ask yourself as you're implementing, do I even need an LLM, right? Can a rules-based approach work? Many times when we think we need a large language model, we find actually as we're building out and doing the product docs, that actually there's a rules-based approach to this that will work even better. But if you do get past this, right, now you might ask yourself, is it in the training data? Is the prompt context window large enough? Is the data changing so fast that I can't use a knowledge base? Or is it static? So that's fairly static, so a knowledge base would work even better than a traditional RAG approach. You'll create a benchmark data set to evaluate your models. Hopefully, if you have the gold standard of previous user requests, you can use those. But in our case, we had to use predicted user requests, which means we created a predicted evaluation harness. We defined our evaluation criteria, we chose a set of models, and we used the simplest model that performs. And as you get better, you rotate underneath other models to keep your uptime. So what other requirements and capabilities did we need? This helps narrow it down further. We needed to support fine-tuning. We allow for feedback, right? As we saw on one of the previous slides, we do allow for prompt feedback. We did not need it to run locally because we've saved as much as we possibly can on inference costs, and that becomes quite cheap, especially when dealing with small bodies of text. We needed to support content moderation and multilingual search. By looking for Spanish, it opened up the door to a whole set of models that we were able to use to cover nearly 100 languages. We did not need to support streaming output because for our inference that was distilled into pills, we didn't need to slow down the request by using a streaming type output to make it seem to the user as if they were getting their information more quickly. And we needed to be SOC 2 compliant. Not all providers are, but it was something that we were looking for. Capabilities, we talked about how search tooling works in RAG, so obviously we needed to add function and tool calling that needed to be built into the LLM and easy to use. We weren't working with agents, so we didn't need multi-step planning or AD key and MCP protocols. We did need to generate a structured output. We were not working with images and are not currently, so we did not need it to have image understanding or generation, which made it easier to pick, right, a wider swath of models. We really wanted a log probability returned, and I'll show you why when we do our eval harness, because it helps give us some confidence in the response, because these are completion engines, and a log probability is essentially its understanding of how well it completed. And we needed it to have real estate domain awareness. So as you go through this, you go through all of these steps, and you choose a model. And you can see here, I had an example of another task that you could use an LLM for, classifying and routing support tickets. And you see here, right, with the throughput being lower and the expectation of the user, we could accept more latency and we could accept more cost. But maybe we want it to be even easier to implement. So on the next slide, I'm going to show you an evaluation harness, a predicted eval set, and I'm going to tell you how I did it. We took a prompt, and what we asked was, for this value, determine which field in the RESO Data Dictionary it belongs. We used easy values. This was not supposed to be complicated. We used active, expecting to hear standard status back. We used ranch, expecting to see architectural style, east-facing, direction faces, and so on, right? Because what we're asking on the demand side is a moderately intelligent model. I'm not asking it to replace a deep subject matter expert. When we did this eval harness, which really proves how embedded the RESO work is now in these open and general purpose LLMs, is we turned their temperature settings down to 0, which means we asked for their response to be as deterministic and not creative as we possibly could. Turning it down to 0, allowing n number of outbound tokens, and being sure we're inside the context window allowed us to create an even playing field for an eval harness across Claude, OpenAI, and Gemini. So if you see here, we took those examples that I talked about from the structure and characteristics groups of property, and we ran them across these models. And we determined, did they pick the right RESO field without reaching out to the outside internet? And what we saw is for the GPT-40 model, we had an 86% accuracy on these easy terms, right? Not overly complicated, not Dasha's from Russia, which was mentioned from Cotality, which is a very difficult colloquialism in real estate. But we found an 86% accuracy amongst things people usually search for. And this shows that GPT-40 not only had the 1.7 dictionary inside its training data, but that it was able to apply that knowledge to new inputs coming in. On the right of the green, you'll see in blue, which is the exponential log probability. So we take the log probability from the token, make it an exponential, which makes it probabilistic, and then reflect that as a percentage to figure out the confidence of the token it responded with. We can see an overly confident set of LLMs here, right, that mostly believe that they're returning the correct information, but we do see a drop-off on the mini model. So as we go through this, the next thing we look at is another pillar, right? This is just accuracy. The GPT-40 model performed very well on this exercise, but unfortunately took 0.8 seconds to return on average. Our cutoff was half a second. So this is not a model that we use internally, although we are extremely excited to test out the 4.1 model that has recently dropped. So as you can see, we take a look at these pillars and this predicted eval harness, and that's where our work is. For us, we are at a very cool inflection point. We have finished our predicted evals, and as our first users come on board, we switch to an actual evaluation harness run in conjunction with our predicted evals. This is what people are searching on today, and this is how we'll get new reflections of accuracy scores. In our evals, we saw things such as no pool, which is a really interesting UI data engineering question that was discovered through our data science evaluations. So we can see how really a lot of this is blurring together, right? A lot of these domains. There's still going to be specialization, but the ability for these teams to work together very well is what's going to make a really good experience. Evals are extremely, extremely important. And if I could say one last thing, on evals, I would just say that what does the maintenance cycle look like for something like this, right? Using general purpose LLMs versus creating your own model. Well, when we have an upgrade like 4.1, we simply increment and rerun our harnesses. It is that simple. So if it works well on the 40 model, we hope it works well on the 4.1, but there is not a long cycle of fixing our models or making them work for other languages. We are piggybacking off the north of $500 million of capital that is being invested into these AI markets, and I encourage you to do the same. We don't have $500 million R&D budgets here, right? We simply don't. But we can utilize other people's models effectively. As a final thing, I just want to say a big thank you to everyone who's supported us in this journey so far, the MLSs, brokers, and vendors who has facilitated data to this over the last 10 months. If it wasn't for you guys, we would not have been able to build this nearly as quickly or nearly as well. So a big thank you to you folks. And that's evals. So thanks, guys.